Hello and welcome to another video. This time I'm taking you through the MAT 2013 questions F to J. So the short little questions get quite difficult in the last five, obviously. They do escalate, they really do. And this one is no exception. But anyway, let's have a look at F. So what do we got here? I mean, when I look at these kind of questions, I immediately get rid of the logarithms. It seems sensible to do. B cubed is C minus 3 and A squared is C plus 5. I don't think I need to explain that step. That to the power of that is that. I shouldn't need to if you're doing math. Okay, so what can I see here? Well, straight away I can see that I can write b to the 4 as a squared from this one. And so now, as b to the 4 is a squared, which is c plus 5, I can say b to the 4 is c plus 5, and b cubed is c minus 3. This makes me very happy because I can eliminate c and then I've just got one equation in b, which is obviously a bonus. Now you've got b to the 4 minus b cubed, I'm just subtracting the two equations, equals 8. Looking at that, it's a quartic, doesn't look very nice, but I think it's instantly solvable if you guess at b equals 2. You do need to be a good guesser with factor theorem. They love throwing in a factor theorem question. If you've ever got a polynomial of degree 3 or 4, they probably want you to use factor theorem and spot an obvious factor. And b equals 2 is an obvious factor here. So we know that b to the 4 minus b cubed minus 8 equals 0 has a factor. As b equals 2 solves this, obviously we can deduce that b minus 2 is a factor. Now please don't think that you have to use long division for something like this. You can do it in your head. B times b cubed would give me b to the 4, but it also gives me a minus 2b cubed, and I only need minus b cubed, so I need to put a plus b squared here. So when I do that times that, I get a b cubed, which with the minus 2b cubed and the b cubed makes minus b cubed. But it also gives me a minus 2b squared, and obviously I don't want any b squared, so I need a 2b here to give me a plus 2b squared. That also gives me a minus 4b, but I don't want any b, so I'm going to have a plus 4 here on the end to give me plus 4b. And look at that, minus 8 on the end, it's worked. So what have we discovered here? We've discovered that this is the same as a linear factor times this. And we've discovered, by the way, that it doesn't look so far like it's contradictory, or that it's satisfied by infinitely many values of a, because we've got one value of b, which is definitely satisfied, 2, which means that a would be 4. Yeah, so we've got one value. Now, is it unique? Well, initially I thought, let's find out how many roots that cubic has, because all cubics have at least one root if they have no turning points, and could have up to 2 or 3 roots, but only if they've got turning points. Yeah, you only get a cubic having 2 or 3 roots, a repeated root there, but possibly 3 roots if it dips below the x-axis, if this has no turning points. So I quickly investigated whether this has any turning points. Now, it wasn't worth it in the end, but there we go, because when you do dy by db here, we're going to get 3b squared plus 2b plus 2. And this, of course, when you set it equal to 0, has no solutions, and you can establish that by very quickly checking the discriminant. The discriminant here is less than 0, because it's going to be equal to 4 minus 4 times 3 times 2, which is less than 0. Hence, this has no turning points, which means it has only one solution. So at first I thought, two values of a then. Yeah, but I didn't read that. Oh, that's so annoying, isn't it? Because clearly the solution to this must be negative. You can see it's not going to be positive because look, we're just adding positive amounts otherwise, and that's never going to equal 0. So the other solution to that, the one solution it's going to have, is definitely going to be a negative b, but we were told that 3 positive numbers satisfy this, so you can't have the negative b corresponding to another value of a, and hence it specifies a uniquely. But yeah, be careful with that, because at first I was like, specified by 2 values of a. No, no, no. Read the question. Read the question. So that was the first thing which could have caught you out. Okay, this one, I like this one. I've got to be honest. I've never found these kind of questions too bad, or this particular one anyway. I didn't find it too bad at all. I found it easier than some of the earlier questions. Okay, so firstly, I didn't write Pn of x down like that. I thought I can add that up because there are n x's, because it goes from 1 all the way up to n. But then you've got like minus 1 plus 2 plus 3 going all the way up to n. Yeah, there's a formula for that. That's triangle numbers. And the formula for that is n times n plus 1 over 2. You should definitely know that little trick for summing the natural numbers. It comes up all the time in these papers. So I made Pn of x that, and I thought, okay, that's cool, because then Pn minus 1 of x is going to be this, but with n minus 1 substituted for n. So you're going to have n minus 1x minus n minus 1 and n times n minus 1. Well, n minus 1 times n, if you like, over 2. Because that's just going to be the same function as was before, but with the subscript notation, we're just going to be trading n for n minus 1s throughout. Also, you can see it works like that because if you had n minus 1, it's only going up to the n minus 1th term. So we're going to add n minus 1, m1 up to n minus 1 here, which is actually that. And there's going to be n minus 1 x's in it. So cool. Okay, now remainder theorem. Use remainder theorem. Don't even start polynomial division. Why would we want to do that? Let's use remainder theorem. Remainder theorem says when you're dividing a function by a linear factor, the quick way of finding the remainder is to find where the x value, where this equals 0, and plug it in there. That's basically it. Let me write it down for you with a quick, if I was dividing this by x plus 3, x plus 2, let's say, I would just plug in minus 2 into here and out would pop the remainder. This is no different. What I'm going to do, as I'm dividing it by Pn minus 1 of x, I'm going to find where this equals 0. I'm going to rearrange this to find what x equals then. You can almost just see it straight away. But what we're going to have n minus 1 is going to cancel on both sides basically, because you're going to have n minus 1x equals n minus 1 n over 2. And so x is n over 2. They cancel. And now we're going to plug that into Pn of x. So Pn of n over 2, and this should just kick out the remainder. We're going to have n times n over 2 minus n, well, let's actually multiply this out. N squared over 2 plus, minus, careful with a sign there, Nichols, minus n over 2. And so what have we got? Well, those first terms cancel, and you got minus n over 2. So the answer is D. Okay, that's my favourite one, by the way, out of the last 5. It was one which really didn't take me too long. H is tricky. H is tricky. Firstly, area bounded by the graphs. If you're like me, you're thinking integrate. I'll just find the area trapped between two graphs by integrating. Integrate top curve minus bottom curve. But you're going to have to find where they intersect first. And I mean, this is a straight line, but it's got lots of square roots of 2 in it. And this, if you just ponder it for a second, you realise, hang on, isn't this the equation of a circle? So we're finding where a line and a circle bound an area. So let's actually start drawing this out, because obviously on lots of these questions, a diagram is hugely useful. Okay, it's a circle, and it's got a radius of root 2, and its centre 0, 0. Cool. What about the line? Well, when y is 0, x is root 2. Oh, great, I've got a common point. And when x is 0, y is going to be root 2 over root 2 minus 1. And root 2 over root 2 minus 1, after we've rationalised the denominator, we're going to times top and bottom by root 2 plus 1. You're going to get 2 plus root 2 over 1. So this is actually 2 plus root 2. So the line intersects the y-axis at 2 plus root 2, which is obviously more than root 2. So it looks something like this. Yeah. My God, that's bad when I'm doing it on here. I need to start using GeoGebra more so I can just copy the diagram over. Now, I think this is hard just because, where does that intersection happen? Now, you could go through the pain of trying to find where the line and the curve intersect, which can be quite painful, but it could be manageable because it is just a quadratic kind of function and a straight line. But it just involves loads and loads of surd manipulation. I didn't do that. I called this angle theta, and I thought, well, if that's theta, then that shaded area is simply going to be a half r squared theta minus a half r squared sine theta. Yeah, and that's from a half AB sine C, and that's from just a half r squared theta if theta's in radians. Now remember though, r here in both cases is root 2, and so we're just going to have root 2 squared, which is 2 times a half. We're going to end up with theta minus sine theta. Great. So I've got a great, lovely little formula here for working out that little segment, which is what I'm looking for. But the trouble is finding theta. Now, this is what I did. And when I looked at the mark scheme, they just kind of said, oh, didn't you see that this was obviously 1, 1? And I thought, no, 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 I didn't see that. I just didn't see it. And when you do see it, it's like, yeah, okay, I see it now. But here's how I'm going to show you that that is actually at the point 1, 1. I said that was theta. But as this is root 2 and this is root 2, this is an isosceles triangle. And so these angles down here are going to be not, well, 180 minus theta divided by 2, which is 90. Let me draw this triangle out bigger, actually, so you can really see what I'm doing. I need to get a better whiteboard where I can use a straight line drawer really nicely because I'm not great on this graphics tablet. Okay, I'm just drawing the triangle out bigger. Okay, what do we know? We know that's theta. We really want to find that theta. Well, this is going to be 90 minus theta over 2, as is this, because that side is the same length as that side. This is obviously 90 minus theta. And this, well, angles on a straight line add up to 180, so I need this to be 90 plus theta over 2. Now those two add up to 180. And that gives me here, once you've added these together and you see you've got a minus theta over 2 plus 180, and we need the 180, I guess this must be theta over 2. Now that at that point I was quite happy because I already know that this is 2 plus root 2 and this is root 2. And so what I can do is I can say, okay, tan of theta over 2 is opposite divided by adjacent, so it's root 2 over 2 plus root 2. And then what I did was I actually used the double angle formulae for tan to find what tan theta equals. Because if I know what tan theta equals, I can definitely find sine theta. It's easy. So I used the double angle formula for tan. And so I said, okay, tan theta is 2 tan theta over 2. Oh, but feel free to mock my method. It's, I like to show you how I did things because, it's more realistic then, when people do it the silly way. So this is the way I did it. I then plugged this in, so I had 2 root 2 over 2 plus root 2 over 1 minus. Now, very quickly in our heads, if we square that, we're going to get 2 over 2 plus root 2 all squared. And I times top and bottom by 2 plus root 2 all squared. And I got 2 root 2 times by 2 plus root 2 over. Now, this is going to be 2 plus root 2 squared. And by the way, 2 plus root 2 squared, hopefully you can do these quickly, but it's going to be 6 plus 4 root 2. Yeah? And so after we take off, because we're going to have 6 plus 4 root 2 here, after we take off the 2, we're going to actually have 4 plus 4 root 2. And look at this. Lo and behold, when you do that times that, you get 4 root 2. That times that, you're going to get 4. And on the bottom, you've got 4 plus 4 root 2. Which is 1. And at that point, I was like, oh my God. Because if tan theta equals 1, theta equals pi over 4. And now the answer drops out immediately. Because remember, I said it was theta minus sine theta from that working out earlier. And so it's pi over 4 minus 1 over root 2, because sine of pi over 4 is 1 over root 2. So there we go. That's how I got that answer. Is it the most effective way? No. But interestingly enough, when I did look at the mark scheme, where a description of how you do this, they just said, well, didn't you notice that 1, 1 lies on the line and on the circle? And the answer is no, I didn't notice. I wish I had noticed. I noticed now. Look, it's obvious now because 1 plus root 2 minus 1. Yeah, that is root 2. I see that x is 1, y is 1 is on that line. And obviously it's on the circle because 1 squared plus 1 squared is 2. Yeah, when you've got that, you know that that intersection occurs there. And it's easy then, I agree, because obviously if it's a 1 across 1 up, that's pi over 4. But no, I didn't notice that. So there we go. Okay, this one's quite fun. I want to show you the diagram I drew for this one because I must admit I really liked my diagram. I was really happy with it. Can I just say though, before I get started on this is crying out for binary. Yeah, if you learn binary for these papers, there's some questions, not the odd question is easier, much easier in binary, and this one would be really not too bad in binary because what we're doing here is we're doubling or we're doubling and adding 1. And in binary, if you double a number and I would expect you to know what binary is. Definitely look into it if you haven't met it before. It's super useful. But if you double a number in binary, you just append a 0. I'll give you a quick example of that. 1101. What is that? That's 2 cubed plus 2 squared plus 1, and that comes to 13, yeah, in denary. Okay, if I double that, I should get 26. Well, let's see if 11010 is 26. That's going to be 2 to the power of 4, which is 16, plus that, which is 8. That would be 4, so we're not adding that, and then plus 2. Okay, 16 plus 8 is 24, plus 2 is 26. See what I mean? Doubling a number, you stick a 0 on the end, and doubling a number and adding 1, you stick a 1 on the end. Now, that makes this question much easier. But I'll leave you to just investigate how this question can be made much easier with binary on your own. But leave me a message in the video at the bottom, like in the YouTube comments, if you want a little bit more instruction on how binary will really help here. It's not the only question. Think about how many times in the mat they ask you just really simple things about functions and doubling and or adding 1 and stuff like that. A lot of them, if you learn binary, there's a really kind of simple approach to them. Anyway, this is what I did for this one. I drew out a cool little diagram. I really liked it because it's a bit of a weird question, isn't it? So f of 1 is 1, and then f of 2 is 1, and then if your k is bigger than or equal to 2, then f of 2k will equal f of k, but also f of 2k plus 1 equals f of k. And you kind of think, that doesn't make sense. Like, that sounds like we're going to be covering a lot of numbers. Well, it does make sense once you start drawing the picture out. So I'm going to start with f of 2 equals 1. Well, let's find out what else equals f of 2. Well, f of 2 is the same as f of 4. And it's also the same as f of 5. Yeah, so I drew it out like this, and I made my diagram. I had a scrap piece of paper, and so I was able to make it quite nice. Give yourself a bit of a gap here when you're drawing out this diagram. It just the idea just suddenly occurred to me because it started creating quite a nice pattern. And you know what it's like when you've got a pattern that gives you something to hang on to. So that one's the same as these two, but from these two I can produce more ones because I'm just looking at the ones at the moment. I'm not looking at the minus ones. I'm ignoring the minus ones, if you like. And so I thought, well, f of 4 is going to be the same as f of 8. But it's also going to be the same as f of 9. And it's also going to be the same as using this one, f of 10, and then doing double and add 1, f of 11. Now look at that. You've got 2, but then you've got 4, 5, then you've got 8, 9, 10, 11. Now let's just do this pattern a couple more times, because with f of 8, that's obviously going to be the same as f of 16 and f of 17. It's also going to be the same as f of 18 and f of 19, and that's from the 9. It's also going to be the same as f of 20 and f of 21, and that's from the 10, and also the same as f of 22 and f of 23. Can you see? I can repeat this argument, and it's just going to list through the numbers. So this allows me to find the gaps, the ones which f of 2 doesn't pick up, which I'm presuming are picked up by f of 3, and I'll show you in a minute that they are. Look, f of 3 is in there. Do you know what I mean? And guess what? When you double 3, and when you double 3 and add 1, that's in there, f of 6 and f of 7. Yeah, so I'm just basically finding a way of counting the ones and counting the minus ones because I've got this beautiful pattern now to depend on. Now, if you look, this is always starting at a power of 2, so the next one's going to be at 32, and then here we had 4, then we had 8, so there's going to be 16 here. Now careful, because we are counting from 32, so 32 plus 16 is 48, but we're going to actually finish on 47. Yeah, and I'll just put dot 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 there. Just like here, there was 8 of them, but 8 plus 16 is 24, but the last one is 23, but there are 8 of them. I call that the fence post problem when you're starting on 0. Let's say you've got 100 meters of fence posts 1 meter apart. You'll need 101 fence posts because you have to start from 0. Okay, so the next one is going to be f of 64. Now here we've got to be careful because, well, let's have a look. We had 8 there, we had 16 here, so we need to add 32 onto that, take away 1. You're going to finish on f of 95. Yeah. Okay, so let's start counting the f of 3's because it's the gaps which I'm kind of interested in some ways. You've got 1 gap there, 2 in between there from 5 to 8, you've got 6 and 7. 4 in here from 12, 13, 14, 15, yeah? and then those are all ones, and then you've got 8, and then you've got 16. Do you see the lovely pattern I'm making here? It's just so nice, it really is. But then you've got 96, 97, 98, 99, and 100. They're all going to be f of 3 ones as well. And so all of these, and it adds up to, what does it add up to? 3, 7, 8 plus 15, 31, 36, yeah? So there's 36 ones which are going to equal minus 1. Yeah, which means there must be 64 numbers from 1 to 100 which equal positive 1, and therefore at the end all I've got to do is 64 minus 36, which is 28. Yeah, all the positive ones plus the negative ones, it equals 28. But yeah, I fully invite you to think about the binary consequences there. You know, you're only using f of 3, especially if you start with f of 3 instead, because obviously 3 in binary is written like that, 2 to the power of 1 plus 2 to the power of 0, which is, obviously 3. And then you're just thinking, okay, how many ways can I add a 0 on the end or add a 1 on the end? So you've got 1, 1, 0, 1, 1, 1, and then you're just going to go up to 100 in binary and just count how many ways there are of doing it. You know, obviously you're going to have 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, 1, 1, 1, 1, 1, 0. You know, it's just going to grow like that so nicely. This is really about binary, this question. And eventually you're going to realize, I hope, that there are 28 ways you can do that. Because was it 28 or 36? Sorry, 36 ways. You'll see that there's 36 ways you can do that. You'll get up to 16, and then you'll need 5 more in the end. But you will need to be aware of what binary is in 100. I hope I didn't spoil that for you there if you were still waiting to do that. Okay, finally this one. God, this one's nasty, isn't it? It's quite nasty. It requires a good diagram, I guess, but there's some rearranging at the end. So for a real number x, we denote x in this square brackets as by the largest integer less than or equal to x. Let n be a natural number. We're working out the integral 2 to the x. Now this is the same for a while. This really helps basically if you draw a diagram. Because if you think about what's going on here, let's think about the graph of 2 to the x. And don't worry, it's not going to end up being an integral. Right. So this is like my x-axis. Right, from 0 to 1, what's happening here? You're doing 2 to the power of 0, which is 1. Now, this bracket then denotes the largest integer, which is below that. It's a floor function, really. We're looking for the largest integer below 2 to the power of 0, and 2 to the power of 0 is 1, and obviously that equals 1. Now, that means that from 0 up to 1, you're going to be going up to there, yeah? Because what we've got here is we're really interested in when we get to, let's say we're at 2 to the power of 0.5. Oh yeah, and can I make this a bit clearer? Move this one over a little bit. So this first value is going to be the interesting bit where you've got log base 2 of 2, which equals 1. Yeah. So 2 to the power of 1. Oh, that's when you're at 2. But 2 to the power of like 0.98, yeah, that is actually when you're doing this ceiling function. Sorry, floor function, which just means round down to the nearest integer. That is actually going to be equal to 1 because, like it says, it's the largest integer less than or equal to whatever this value is. So that is actually 1. It's not until you get to x is 1 that you suddenly are going to be jumping up. Yeah. And then from x is 1, think about what's happening here. 2 to the power of 1, but we want to work out when we get to 3, yeah? Like, I don't know, maybe it's about 2 to the power of 1.5. It's definitely not 2 squared. 2 squared, we're at 4. But wherever we get to 3, well, how do you can work out, like, when you're going to get to 3? You take logs of both sides, don't you? And x is log base 2 of 3. And that's where these logarithms come in. So x equals log base 2 of 3. That is where you're going to be going up to, where this equals, and let's just make sure we've got the y coordinates right. This is 1, and then this is going to be at 2. And then you're going to have a similar thing up to 3, because it's going to be basically where you've got a bit like this expression here, where we had 2 to the power of x equals 3. We're going to now have to do it for 2 to the power of x equals 5. And essentially 2 to the power of x equals 4, but that's obvious because x equals 2. Let's write it down. 2 to the power of x equals 4. X obviously equals 2 there. And then 2 to the power of 5, well, x is obviously going to be log base 2 of 5. And it's handy, actually, if rather than writing log base 2 of 3, we start writing it all in terms of logs. And that's why I was tempted to write that down as log base 2 of 2, log base 2 of 3, log base 2 of 4. Now you've got the pattern. Do you know what I mean? That's what's actually going to go on. Then it's going to be log base 2 of 5. And this is going to change each time, basically, as you're going up through the numbers. So it's all lining up nicely. Okay, so what have we got? It's nice if you actually think about it with n as an actual value here, and that's what I did. I thought about n at 32, yeah? So that helped me anyway, it seemed to be. So going up to 32, we're going to be at 32, obviously. These are the things we're setting equal 2 to the power of x equal to. So when 2 to the power of x equals 32, obviously x is 5. But let's write that down as log base 2 of 32, yeah? But remember that it's going to be at 31, this last line. And if you like, that's just going to be a dot. If you see what I mean, because log base 2 of 5, well, we haven't got any values there yet, really. The line is going to be stretched out before it. And then we can see for this integral, we just need to find the areas of all of these rectangles. That's what we're looking for, the areas of all of those rectangles, all the way up to the top. So let's actually write it down. We've got between 0 and n, the ceiling of 2 to the power of x dx, well, it's going to be equal to 1 times log base 2 of 2. Minus, if you like, and it helps if you know, for like being systematic. 0 is actually log base 2 of 1. Basically, log base anything of 1 is 0. And then we get this lovely pattern because we can say 1 times log base 2 of 2 minus log base 2 of 1. Because this is what we're going to have to do for all the other ones. Plus 2 times log base 2 of 3. Really, now you've cracked the question. You've just got to be careful with how you do the rest of it. Log base 2 of 3 minus log base 2 of 2 plus dot dot dot, and generally you're going to be going up to, now if you look, this is always the same number as that one in there. So, and also, like I said, we've got to go up to n 2 to the n minus 1 here, times by log base 2, and let me just move the screen over so I've got plenty of space. Log base 2 of 2 to the power of m. Oh, yeah, let's write it in the same format as I had before. Log base 2 of 2 to the power of n minus log base 2 of 2 to the power of n take away 1. Cool. And then basically I just got to turn this into the answer, which is easier said than done. What we're going to get here, clearly this is log 2. Let's stop writing down base 2. We know it's all base 2. So we're just doing the division of logs there. But plus 2 log 3 over 2 plus dot 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 going all the way up to 2 to the n minus 1 log 2 to the n over 2 to the n minus 1. Cool. Now, why does this get quite nice? Well, let's just write it as a single logarithm now. We could write this as log of 2 over 1 times by 3 over 2 but squared, so we could have it as 3 squared over 2 squared, times by, if you like, the next term's going to be, you know, basically increase this, increase that, 4 over 3 cubed, dot, 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 all the way up to 2 to the n over 2 to the n minus 1 to the power of 2 to the n minus 1. That's just going to fly up there as a power. and that's a big log expression. And then we can actually do some serious cancelling now, lots and lots of cancelling, because look at this, the 3 squared cancels with the 3 cubed, if you like. We're going to get the 2 cancelling with a 2, we're going to get the 4 cubed, and the 3 squared hasn't cancelled with the 3 cubed, obviously it's going to leave a 3 there, and so what we're going to have is, let me just explain this as I might even have an intermediate line here. So what have we got? You've got log of we're going to have a 1 over 3 times by, and a 1 over 2. I've missed a 1 over 2. That's why I'm getting confused. The 2 squared, I've missed that 2 squared. So you're going to have 1 over 1, if you like, times by 1 over 2, times by 1 over 3, times by all the way up to 1 over 2 to the n minus 1. But let's not forget that this last term isn't going to cancel. So that's going to be 2 to the n to the power of 2 to the n minus 1. Wow, that's a really, really, really complicated expression. So what we can say is that's the same as 2 to the n minus 1 factorial on the bottom, because that's the nature of factorial. And on the top, you've got 2 to the power of, so that's just going to get times by that. And so that's going to be 2 to the n. Wow, I've really made a mess of this. 2 to the n to the 2 to the n minus 1. Yeah, so I'm just pointing out that at the moment. Oh, it's getting really messy, my working here. And so, finally, whew, what does that give us? Well, when we do that as a power, we can actually sort of break this up a little bit if we multiply top and bottom by 2 to the n. So I'm just going to try and multiply top and bottom by 2 to the n, because then I'm going to have 2 to the n factorial on the bottom, which I think is the way their answer's written down. And if I times this by 2 to the n, I've got 2 to the n times 2 to the n, well, to the power of 2 to the n, take away 1. Let me make that very clear, because I'm getting a series of indices. Trying to make it very clear, I'm struggling. And if I times that by 2 to the n, well, what we've got here is, if you like, something to the power of 1 times that, we add the powers, so you get 2 to the n to the power of 2 to the n. And is that one of the answers? It's a horrible question, it really is. Okay, I've just got to sort out the division, it would seem. And if I just break this up, we are going to get there. I'm certain we're going to get there. This is the same as log of 2 to the n. And then I can flick that 2 to the n down, which is nice. Minus log of 2 to the n factorial. Yeah. And then we can, actually cancel this, because remember, this is log base 2. So that's n times 2 to the n minus log of 2 to the n factorial. Hope you got a better way than me of doing that one, because it doesn't seem like the nicest question. It really doesn't. But yeah, that's why I believe it's the answer to part B. But yeah, wow, what a question. Okay, hope you found these videos useful. Hopefully I've given you some ideas for questions. These are just my ideas. I don't claim to be the best at this or even half decent at it, but just my ideas. That's what I'm thinking. Okay, well done everybody. Thanks for listening, and all the best.